So I'm here today to tell you about chaos engineering so that you can improve your system's resistance to failures. And how I get to talk about this? So I work at Erlang Solutions, and for last year and a half, I've been involved in developing a continuous load testing tool, and this is how we came across chaos engineering as such, starting experimenting with it. So we read some books, some blog posts. So what I have to tell you, what I have to tell you about today is based on my experiences as well as knowledge that we gathered over time. So let's start with some basic questions: what, why, and how. And if you think about today's systems, we very often deal with large distributed complex systems which are based on microservice architecture, and to serve a single request, multiple services have to be contacted. And it's often the case that big companies in big systems, no longer one person is able to capture the system as a whole. And that's why we can say that chaos is inherent in them, whether we want it or not. And then these different microservices may function properly on their own. They may be shipped by different teams, may be tested in isolation, then integrated on some integration platform, and then they come live. And then the interactions between them, especially when compounded with some real-world events like server crashes, disk failures, net splits, may lead to unpredictable outcomes. And to give you an example, let's imagine that we have some client getting into our system, and it calls microservice A, then microservice A calls B, then calls C, C calls D, A calls E, and at some point C crashes, A is not able to satisfy the request, but it has fallback in place, which is F. So it calls fallback, but it turns out that the fallback is misconfigured. Somehow the bad configuration made it to the production, builds up the queue because it's not able to handle the load of the request that C was, and finally crashes. And chaos engineering is about experimenting on a system, provoking scenarios like this one, so that we learn the system behavior in turbulent conditions. In formal terms, chaos engineering is a discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. So it's empirical because it says about experimenting. It's also about learning system behavior because we have the building confidence in it. And finally, it's about experimenting at scale because it tells about turbulent conditions in production. So this scenario could be chaos engineering scenario in which we deliberately, on purpose, disrupt C, observe the system, and we learn the weakness related to the fallback. And in chaos engineering, we focus more on exploring than to testing assertions. So we are aimed at discovering and observing our system and learning what it does if something bad happens. Okay, let's have a look at the why question. What's the rationale behind the whole concept? First is about building trust. Today we have great development velocity and complexity in some systems, and as I said, it may happen that one person is no longer able to capture the system as a whole, so we don't have this trust in the first place, especially when we have different components and they are shipped and brought live on a daily basis, and that's why we need to build that trust. So this is where chaos engineering helps. It's about being proactive because we want to discover some systemic weaknesses before they manifest system-wide, because there is some hidden vulnerability in our system. And finally, it may be cheaper to put some users at risk of experiencing poor quality of our service than to have entire business taken down because of a hidden bug in our system. And let's have a look how to actually practice it, but before we get into it, let's look at steady state first. So system steady state refers to some property of a system which it tends to maintain within a certain range of values or pattern over time. If our system is the human body, we can say, and that the property is the internal body temperature. By observing the body temperature, we can say whether the body is in steady state. So it's roughly when our body temperature is around 37 Celsius degrees. So the steady state refer to the system's normal operation. To give you a concrete example, this is the graph representing request response time of some system, and you can see that it is around 40 milliseconds. Because we have been observing the system for a long time, we have learned that this is the normal operation of the system, the steady state. And now, if you look at the second one, we have some spikes reaching up to 120 milliseconds. And because we previously learned what is the steady state, now we know that our system is out of the steady state, that something bad is happening. And chaosprinciples.org defines four steps to practice the discipline. And the first one is to define the steady state of your system. In other words, it's about understanding some measurable output of a system indicating its normal behavior. Once we have that, the second step is to hypothesize that the steady state will continue if we break something in our system, if we introduce so-called variables. And this is the third step, which is about introducing these variables, real-world events like server crashes, disk failures, net splits, and maybe other things, and having them in place in our system, we can learn the behavior that the system exhibits when we have these variables enabled. And finally, the final step is to try to disprove the hypothesis by looking at the difference between the steady state and the output of the metric that we picked, that we actually based our steady state on. And if we are able to see the difference, we have uncovered a weakness and we have target for improvement. And if there is no difference or there is acceptable one, we learned that the system is able to withstand a given turbulent condition associated with the variable we introduced. So we can say that the harder it is to disrupt the steady state, the more confidence we have in the behavior of the system. Let's have a look at some example from the Netflix platform, how they do it. So let's imagine that they have a client which calls the gateway, then gateway calls API, and API finally reaches ratings service. The ratings service is responsible for calculating some rates of movies that you see when you are looking at different movies in the app. And what they would do and they would ask a question how API handles failure of the ratings service. So this is the one of the chaos engineering scenarios they would run, so that they would ask this question, and then using CHAP, which is chaos automation platform they have, they would spawn two additional clusters of the API service. One is the control one, and the second one is the experimental one. And what they would do next, they would decorate the requests going through the gateway so that some fraction of them goes through the experimental cluster, the other fraction would go through the control cluster, and the rest would go the normal path. Then they would scale this the number of requests going through these different clusters appropriately, so that they minimize the blast radius, because they want as small number of users as possible experience any failure. And finally, they would introduce this failure, which is about simulating that the ratings service has failed. And it means that all the users going through this experimental cluster would not be able to get the output from the rating service. And if we think how this maps to these 4 principles, so this question is the base for the hypothesis. So they could hypothesize that API will behave, let's say, well if rating service is not available, meaning that the user will get a response with some data missing, but they can live with that. They know they are steady state because they have been observing some metric of the API cluster over time, so they have learned what the steady state is, and then they would introduce some variable into the system, which is the simulation of the ratings failure, and finally they would compare the outcomes of this metric that was based for the steady state and know and actually learn what's how the system behaves if there is this kind of a failure. And this brings us to the second section of this talk. So you saw what are the basic principles, and now I would like to share with you my experiences, or maybe our team experiences with applying chaos engineering principles to one of our systems that we develop at Erlang Solutions. So what we do, we have a messaging server, Mongoose IM, which is XMPP messaging server, which allows clients to exchange messages, like for instant messaging. And it connects to it talks to the authentication service to authenticate these clients. It talks to some database to store messages the users exchange, so that there is an archive feature. And finally, in some installation, it would log some events that happen in the server, like user logged in, user enabled something to the streaming service, like Kafka. And now, when the system is running, something wrong may happen on the connection to the authentication service. For some reason, we may not be able to talk to the authentication service because of network glitch, or the database may become not reachable, or we get some data that we cannot persist and we have an error at this place, or something similar may happen with the streaming service. And all these places, and now we can simulate these failures in our system, and all these places in the code actually literally are called injection points. So these are the places where we can enable some faults. We can simulate that these bad things happen. And having all this, we can set some hypothesis that our system will behave in a certain way given one of these turbulent conditions occurs. And we simulated these failures by injecting them into the Erlang VM running our server. And before I get to the actual techniques we used to inject the faults, let's have a look at what was the environment we were running our chaos engineering in. So basically, we use our load testing infrastructure to run the experiments, and we have a scenario which describes a load test, which is a code that describes the users that connect to our server, that emulates the users, and they do different stuff. We feed load generator with this scenario, which in turn, we put this scenario into the load generator, which in turn stresses the server, and we learn the measurable output of the system, and this is our steady state. And this is our control load test. Then we take the same load test scenario, we run the same load test, but this time we add another component which inject faults. And this is our experimental load test with some hypothesis set. And at the end, we compare the outputs, the metrics that we base steady state on in the first place. And in our particular system, we treat two metrics as indicators of steady state. The first one is the time to deliver, which tells us the time between the client send a message, and this is the time that passes between the client sends a message and recipient gets it. And the second one is the session count, This is the server-side metric, which indicates how many sessions are there in the server. So in total, we have around 110,000 sessions in the server on 3 nodes, and they fluctuate a little bit because some fraction of users reconnect during the load test. And the first hypothesis within the chaos engineering frame we said was that failure to write to the database won't disrupt the service, meaning that if we cannot write to the database, we are still able to deliver the core functionality, which is allowing the users exchanging messages. That was the first assumption we set. And in Elixir or Erlang-based systems, you would have workers connecting to the database. In our case, that was Cassandra, and pool of supervisors on top of them. And to simulate this failure that we cannot write to the database, you would kill the workers at interval. You would kill the workers at interval while the system is running. And this is the code that actually implements this fault. So what we would do, we would define kill pool anonymous function that would basically get all the workers that connect to the Cassandra, pick the random one and kill it. And having this fun, we would wrap it into another one, which would basically kill random worker every 15 milliseconds and then call itself recursively. And finally, we would wrap that into a function, which is our fault. So once we spawn this function, we start the experiment, and when we are done, we kill it. And what we learned from such an experiment. So this is the time to deliver metric. This is where the chaos started, and we saw that the performance was better in a sense because the time to deliver dropped. Then when we looked at another metric that indicated the number of archived messages, so in other words, the number of writes to the database, successful writes, it sort of stayed the same, which was a little bit strange because we thought that we were not able to write to the database because we were killing workers, but the other metric was telling us something different. So we came to implement some client-side metric to understand how many messages are read from the archive, because the clients would read the messages in the fashion that they would read chunk of messages, remember the timestamp of the last message they read, and then after some time would come again and read from that timestamp, which effectively means that they would read all the messages they would have in the archive associated to the account. And we see that just a few minutes after the chaos started, there was a significant drop in the number of messages read. So the learnings were that we had wrong metric indicated how many messages were actually stored in the archive. So the previous one on this slide, the implementation of this metric was wrong. This is what we discovered. So we had wrong data here. And we also learned that if we have this kind of failure in our system where we can't write to the database, the performance is preserved and the core functionality is still there. So that was good. And the other thing was that the database operations were simply dropped, so the server had less work to do. That's why we saw the increase in performance. So quite interesting learnings about the system for us. Okay. Another hypothesis we said was that if there is a delay on the connection to the authentication service, the users will be still able to log in. So another metric indicating steady state for us was the number of connected users. And similarly, as with the database, in the database case, you would have a pool of workers connecting to the authentication service, supervisor on top of them, and every time someone logs into the server calls the authentication service. And to simulate this kind of failure, you would add a delay at the worker level. And this is the code that we use to achieve this goal. So first, have a look at this delay auth fun. So basically, we use the mocking technique. What we did, we replaced the original function that would call the authentication service with a made-up one that would have delay added in it. And what we would do, using the Mac library, which is the Erlang library for mocking, would install a new mock. Mongoose Auth is the module responsible for authentication. And we would mock the authenticate function and provide our own that would take user and a password, the delay one, and the delay one would basically sleep for 100 milliseconds, this is the delay, and call the original function. This is what the make pass-through does. So it would call the original authentication function from the Mongoose Auth. And we would take this composition of anonymous functions and put into a process, spawn it. This is how we run our fault. Once we are done, we would stop it. And this is what we learned. This is where the chaos started, and you can see that there is a drop in the number of sessions on one of the servers because we ran this fault just on one server. And so it dropped to some level, but because just fraction of users would reconnect to the server. So this is why it didn't go down to 0. And these are the not affected nodes, the affected one. And this is another graph confirming that actually the number of logins per second dropped at one node. And what we learned from this experiment was that 100 millisecond delay at that point in code was enough to prevent users from logging in. So this is something we need to investigate further, as we didn't actually understand it properly yet. And the other thing we discovered was that in the load generator we had a bug that because you would expect that the user that cannot connect to one server would eventually pick another one and connect to it, because we thought we had load balancing in place, but in fact we didn't. Actually, it didn't work. So the users would try reconnect to the same server all the time. So these were the learnings from this experiment for us. And the third experiment we ran was, the third hypothesis we said was that spikes in message rate sent to Kafka want to disrupt the service. So we send records to Kafka on different events in the server. For example, when user log in, when it sets some setting. And to simulate this fault, you would spawn an internal process, a flutter, that would stress Kafka with some made-up messages and just send it to the Kafka layer internally. And this is how we would basically verify this hypothesis. And to achieve that, we would define a produce fun that would construct some random message and then call the API to send stuff to Kafka. And then we would construct another fun that would call produce 50,000 times, then sleep for some time and call itself recursively. So this is how we simulated like spikes in messages sent to the Kafka layer. And again, you would take this composition of anonymous functions, spawn it in a separate process, and once we are done, we would kill that process, encapsulating default. And this time, this is where the chaos started. We learned that it has no, that the performance is preserved, the core functionality we're looking at is still there, and this is another graph confirming that we really had huge increase in number of messages sent to Kafka. So we learned that our system is able to withstand this kind of, maybe not failure, but situation in which the Kafka layer has to deal with much more messages that we expected it to do. And all these fault injections techniques you saw basically didn't require any change to the existing code base, meaning that you wouldn't have to recompile anything. You would just construct anonymous functions, spawn a process, and once you are done with experimenting, you will kill it. And we were playing with it by writing the code directly in the shell, but this is not handy when you want to automate things. And you make use of the RPC Erlang module that allows you to call remote functions on the affected node, or spawn remote processes using the node spawn API. And this is similar to what we did. Defaults could also be weaved into the code in the sense that the messages or different events could carry along some metadata with it that would trigger these faults. This is how Netflix approaches the problem, but it was not required in our case, and this is why we didn't have to tamper with the existing code base, so no recompilation was needed. And so we learned some things about chaos engineering when we were experimenting on our system, and then now we have ambition to automate the whole process. So we designed some solutions, some system that would basically run chaos engineering experiments for us that could be pluggable in our continuous integration pipeline. And in this section, I would like to share our thoughts, our design of this kind of a system. So short recap. So to run these experiments, we make use of our load testing infrastructure. We run 2 load tests. One is the control one, the other one is the experimental one with some hypothesis set. And the second one make use of the fault injection component. The faults are being injected into the server, and we compare some measurable output to see whether there's a difference in some key business metric. And this is for us chaos experiment. And this is the new component we are working on, which is chaos automation tool. We call it Typhoon. And this is just an Elixir application, which is Phoenix-based. It comes with a front end and a back end. And on the back end, we have 3 components: chaos manager, fault injection component, and infrastructure component. And the infrastructure one brings 2 models. I forgot to say in the beginning that at the beginning that we run our load test in a Docker environment. So for every load test, we spin off a bunch of containers running different services, and when we are done, we basically tidy everything up and store some metrics on the side. So the test setup defines some configuration files for the services that we run in the load test, Docker images, some metadata, and while test topology describes the load test when it's running. So like services names, like IP addresses, ports that got assigned to different services and things like that. And then we have fault injection component that defines fault protocol, which is an interface of all faults. It's an Elixir protocol. It manages collection of faults, and this is the extension point so that users can add new faults to the system if they want to experiment with something that is not yet covered. And it also, and my fault is an example fault. And finally, we have chaos manager, which brings experiment model, which holds things like IDs of the load test, the setup, the list of faults, and faults offsets, so that it knows when a particular fault is to be injected. And if you were to work with this system, you would configure your load test, set up your faults, their parameters, and Chaos Manager would create an experiment out of it, run the control load test through the infrastructure component. You would learn the steady state, and then you would run another load test, the experimental one, and using the topology and the list of faults, it would inject them through the fault injection component. You would learn the behavior of the system under these particular faults, and you would be able to compare the two and either build the confidence in your system or find the weakness of it. And few Elixir bits. So this is very basic implementation. This is a very basic implementation of the protocol, of default protocol we have. It just defines one function apply. So it takes. So we treat faults as data types, as structs. So it would take the default and the ID of the test to apply the fault to. And this is how the example implementation looks like. So we use ecto to verify parameters of faults coming from the UI and to build the structs representing defaults. And each fault is to implement the fault protocol. And to wrap up, I hope that you got to know some basics of the chaos engineering as a concept. You have an idea how to apply it to beam-based systems, and you would know how to automate the thing. And I encourage you to go and try it. It's for everyone, not only for Netflix or Google or companies like Facebook. And try to play with the basic techniques, and if it works for you, add it to your continuous integration pipeline so that you bring your software to another level. This is all I have for you. Thank you.
So we have plenty of time for questions.
Hello. So the version of the chaos engineering that you did doesn't actually work with live on the production system, right? But in a Docker
that's correct. So we abused the rules a little bit. I forgot to mention that. But it's not about sticking strictly to the rules. It's still, we can still benefit from it. So our business case, so to speak, is that we have an open source XMPP server which clients install at their premises or somewhere, and then it would be hard to experiment there. So we know different architectures that they would use. So we try to so we have like a, let's say, common one, and we try to continuously experiment on our system at our load testing infrastructure, because it is the setup that resembles the live system, the production one. So we're trying to be as close as possible, but for us it's not a live system.
Thank you. And very small related question is, when would you actually start using this when you develop a new system? Like, when is a system complex enough, in your opinion, to start spending some time making this?
If you want to be strict, then you would have to practice chaos engineering when you are alive. But during the development phase, I would say once you have some stable load testing environment, then you could have some simple scripts that would, let's say, kill a node or something. And the other thing you would need to have is some scripts for metrics, so that you can easily store them and then fetch the historical one and compare the two sets of metrics, so that you know, so that you can judge whether the experiment discovered something or not.